Okay, let's finish up chapter 14. I'm going to do 14.4 on buoyancy and 14.5 on Newell's principle. And try to do a little demo at the end as best as I can here to demonstrate landing and flow. Buoyancy. Buoyancy, when you think of buoyancy, a lot of times you just think, does it float or not? Is something buoyant? Does it sink like a rock or not? If something's buoyant, it tends to want to float. Well, what I will say is, in general, buoyancy, a buoyant force is exerted up on all objects in a fluid. Now, I will say this, I will say, in the presence of a gravity well. Give me just a minute. Somebody's beeping. I'm not sure if they're at my house or not. I'm at the barn. Well, my dogs wouldn't move, so I had to move the dog. So as long as there's a gravity well, in other words, if it's like sitting on the Earth and under the influence of gravity, if we were in the International Space Station undergoing free fall, so you know, there really wouldn't be a buoyant force on you because gravity's not pulling down in the direction on that fluid. But in a gravity well where you're getting pulled down, it's valid. Now, what would cause that? Well, let's look at our container here. And in this container, we got some fluid. We'll call it water. It can be whatever we want. And let's draw something inside here. The book does a cylinder. It doesn't matter. It can be a rock. It can be a box. It can be, my hopes and dreams for LR sinking due to COVID. That would have to make them tangible. I guess I'd write them down, put them in a box, and throw it in the lake and see it sink to the bottom. But what's going on is a buoyant force is always going to be exerted on objects. It's going to be exerted up. This buoyant force is. Now, we know down on it, there's a force of gravity. F sub G. F sub B be the buoyant force on that object. Now, the question is, what causes a buoyant force? And if you really want to think about what causes it, it's the fact that the pressure is everywhere the same. So let's use this water blue for the water. Now, at this height, there's a pressure on it. At this height, there's pressures on it. And here, there's pressures on it. Now, what you notice is, if these pressures, remember that's just force over an area, these here cancel each other. So really, you're just looking at pressure pushing down at the top and the pressure pushing up on the bottom. Now, we know pressure is a function of depth, rho GH. Call this P at the top, P at the bottom. And because pressure is rho GH, rho is the density of the fluid, G is gravity, H is, or D, they use D. Let's use D. D is the depth in the fluid. The further you go down, you got more pressure. And at any point, pressure is going to be the same all on something. It's just on that surface of that object. So that tells you then, since D is greater for pressure at the bottom, it's deeper. Pressure at the bottom, greater pressure at the top. So these vectors add together, there's some left over on the bottom still pushing up. So this implies a net force greater than 0 pushing up on that body, because these forces here and these forces here add up with each other. Okay, they add up. And since these are bigger, because it's less deep at the top than it is on the bottom, there's more pressure pushing up, more force pushing up on these same areas. So there's a force pushing up. And what do we call that? This is the buoyant force. And you've seen it. You know it. Further you go down, actually it gets, you've seen this buoyant force take like a ball and push underwater, and somebody comes near you, let it go, and it goes whap right in your face, right? You've never done that. I, of course, saw other people do it. Never do it myself. But it's interesting to watch, of course, right? Rather than do it yourself. This buoyant force is what causes it. This difference in pressure at the top and the bottom. Now the question is, what's that buoyant force equal to? What's it equal to? Well, actually, it's equal to the weight of the fluid displaced. So if it's the weight of the fluid displaced, as long as this is underwater, doesn't matter from at the bottom of this lake or bucket or near the top, as long as the whole thing's underwater, a buoyant force does not depend on depth. Now, I could say to first order, you take into account the difference in densities of the water at the top and the bottom, maybe at near the top and near way deep. Yeah, it could vary a little bit, but in general, we say it doesn't. You know, within a good, actually 98, 99% probability, 99% correct percent difference. It doesn't depend on depth. Does not depend on depth. And again, this is assuming water is not moving, the fluid's not moving as well. We'll get into that next section. Now, this buoyant force equal to the weight of the fluid displaced. That means that the buoyant force, how would you find the weight of that fluid displaced? Well, you know that we know the density of the water. Density of the water is rho. This is, let me do a little better, rho. Rho is mass per unit volume. So if we multiply it times its volume, we'll get the mass. So let's take the volume of the object in the fluid. Now this is really a mass, because this is mass. Remember, rho is mass over volume. We did that last time. And now we got mass times over volume times volume. We're left with mass. And now how do we find the weight of it, or the force from it? We multiply it times g. At this point. So times g. So the weight of the fluid displaced, weight is mg. We find the mass of that object times g. And this is the weight of the object, which is equal to the buoyant force. It's equal to the buoyant force. Now, sometimes you might have heard this called Archimedes' principle. Archimedes' principle. The book doesn't go into Archimedes' principles too much. What I will say is, if it's the weight of the fluid displaced, it's the volume of that object. So if you had a pound of gold and threw it in the water, the buoyant force on that up would it be depend on how big that pound of gold is. So you got a pound of silver. Well, they have slightly different densities. So a pound of silver, if you throw it in water, would have a different buoyant force on it. Because its volume, since it's a slightly different density, its volume's different. Since its volume's different, and I'm not mistaken, the volume of a pound of gold is bigger because it's less dense than gold. Since that volume is bigger, if you threw it in water, it would displace more fluid. In other words, it would push more fluid. If you filled it right to the top, it would make more fluid fall over the edge. That's what displace means. How much water got either pushed up, or if it's right at the top, how much water would spill over, we would say. So, interesting. Now, who came up with that idea? Archimedes. Now, you may or may not know the story of Archimedes' principle. I'll basically tell you a story, of course, that's been passed down for generations. But the basic gist of the story is this. There was a king, and Archimedes was, he was probably one of the smartest guys in the Greek-Roman time frame scientifically. Archimedes developed what's called Archimedes' screw, which pulled water up from a deep hole. Military weapons. Greek fire is supposedly was probably tar and some other thing mixed together that they would throw out, would, stick to things and float on the water. It's attributed to Archimedes. So Archimedes was asked to find if this crown was pure gold. King, where he was at, had asked the crown to be made. He got it. He wasn't really sure if the guy made it out of pure gold or not. It's just something didn't seem right. So he asked Archimedes, figured out. Well, he did, and he tried, and he couldn't do a dead end. Lots of times in science you try everything. Well, I think this is true. Wrong. All the consensus of all the scientists were you do this, and it really didn't tell. Scientific consensus is not science. So he kept trying some things, couldn't figure it out. So one day he asked his servant to draw him a bath. So the servant, when he drew him his bath, he filled it like right almost to the tops. Archimedes, he was tired, wasn't paying much attention, got in, water overflows, he looks around, and he thought, and the story is, he got so excited because now he had a way of solving a problem if the crown was made of pure gold or not. He runs down the street, naked as a jaybird, is the story, and runs to the king, yelling, "Eureka, Eureka!" And then whatever in Greek you say, I figured it out. But the term Eureka in science is like an aha moment. It's from the old Archimedes story. Well, he goes to the king. They put a gown on him. You don't want an old man like Archimedes going in front of the king naked. Not a good sight, right? And he goes to the king and said, "Weigh the crown." So they weighed the crown. They had scales in. And said, all right. So they figured out how many pounds or whatever unit they used back then for it of gold. He said, all right, bring me pure gold of the exact weight. So they basically took one of those balance scales, fulcrum here and crown here, pure gold here. So they got that equal. So they were equal and balanced. So he took a bucket like this and had another bucket. And this was the overflow bucket. This had the water in it. Inside here, he placed the block of pure gold. Gold was red. Didn't you know that? So this was pure gold. Now, when that happened, overflow, it got pushed up, some went out, so now you had some water here. So what they did was they measured how much water spilled over. And you can just take that and put it into a graduated cylinder, right? Or just something to measure how high it goes on this tube, right? And then they did the same thing for the crown. That's the crown. All right. When he puts the crown in there, it spills over as well. And if the crown was pure gold, what would happen to the spillover amount? Well, it'd be the same, right? Problem is, gold is very, very dense. Lots of times people, substitute lead in it. 24 karat gold or pure gold is also very soft. That's the reason you don't make jewelry out of 24 karat gold, because it would just kind of tear through. It's very malleable. More water was there than was in the one with the pure gold. There was a different amount of water is the key. There's a different amount of water. Was the crown made of pure gold? No, because the buoyant force, which is equal to the weight of that fluid displaced, was different. You could actually have measured this water here, the weight of it, and measured that buoyant force of each. And if the buoyant force is different, you did not have pure gold. And that's what happened. According to the legend or the story, off with his head, right? He dead. They kill him. All right. So that's Archimedes' principle, is kind of the beginnings of this idea here. All right. And, it's based on how much volume it takes up, and that volume would be equal to overflow. And from this, though, you can get an idea on why things sink or float or not. Or float on top of them. Boats float. Have you ever wondered how, like a really heavy boat, it weighs hundreds of pounds, thousands of pounds. Stick it in the water, bloop, it floats really good. Just hit that button or crank that motor, and off you go, catching your fish, pulling somebody jet ski or water skiing or whatever. Get on a jet ski. Out of the jet ski, you can't curl a jet ski. It's too heavy. Nobody in this class can. Even Sean can. But, it floats. How can it float? Well, it's based on this idea a little bit. So what you want to say is, object floats or sinks. If, and this is key, it floats if the buoyant force is greater than the weight. Force due to gravity, pulling down on it. Right here, force due to gravity pulling down, force of buoyant force of it. If this is greater, it'll float on top of the water. It sinks. Just like Leonardo DiCaprio in Titanic. Oh, way he sunk at everything. Best part of the movie, right, guys? It sinks if the force of gravity is greater than the buoyant force. Now, if you've seen Leonardo DiCaprio lately, he's a big boy now. You know what I mean? He's a big one. And, fat floats. It's less dense than water. We'll get into densities here in a minute. Maybe it doesn't sink so fast, or maybe it doesn't sink at all. They did the movie now. They did a remake of it. Now, it stays at the same depth if the buoyant force equals the weight of it. Buoyant force equals the weight. That's how you say if something sinks or not, or floats, or stays the same depth relative to this. Now, you've also may have seen this in terms of density. So, in terms of density, I'll put this in terms of force. In terms of density of the fluid, you got to look at it like this, because buoyant force is proportional to the density of the fluid. Right here it shows. And what you can say is, if the density of the object is less than the density of the fluid, it sinks if the density of the object is greater than the density of the fluid. And it stays right at the same depth if the density of the object equals the density of the fluid. Alright, so that's it in terms of density. Now, let's take an example of something that can modulate its density. Modulate means change. At will, to make it float, go to the top, sink, or stay at the same depth. One example is a submarine, right? You've seen submarines. They'll basically rise to the surface. If you hunt for Red October, it comes out like that. How does it do that? Well, it's got to make its density less than the ocean water. So what's it do? It pumps out ocean water. It has basically ballast, or basically, ballast was rocks in the bottom of ships for many years to keep them upright so they didn't want to tip over, especially because they were high. Now, that ballast water they pump out, it's less dense. There's less weight inside the sub. So its density decreases, and it starts rising. and of course, as the density decreases more, it gets it goes up even faster. How do you get a sub to sink? Well, it sucks in water. It pumps in water, or just opens a valve and lets water in, and it fills up these ballast tanks. How does a sub stay at the exact same depth? Well, it gets to a point where its density, based on how much ballast water came in, equals the density of the ocean around it. And at that point, they quit letting any water in, and it'll just sit there at that altitude. And they can just, if they want to, turn on the little prop and go forward, or whatever they use, jets or whatever. By the way, our subs are so quiet. It's amazing compared to anyone else's in the world. Now, what's an animal that does that? Well, a fish. What do fish do? Well, they actually have a swim bladder, it's called. What is that swim bladder? Basically, it kind of lets water into it, pumps water out of it, and it can help that fish to change depths in that water. And it's pretty amazing. It kind of does that. If it wants to stay where it's at, it just gets to a point it wants to be and stops letting any fluid or water into that swim bladder. That's how things float or sink. Now, there's some examples in your book. The example problems here, do them. They're not that hard. Make sure you do them. They do think about boats as well. Remember, density is mass over volume. So you got to take into account density there. All right. Next, we want to talk about fluid dynamics. My gosh, this is a hard topic. So we're only going to talk about Bernoulli's principle in regards to this. Fluid dynamics is actually, it's a very cool subject, I think. It's about time to break out the acetone, I think. Yeah, let's break out the acetone. Doggies are barking at something. Maybe the neighbor's cow got too close to us or whatever. The neighbor's cows get too close to the fence. The dogs get all, they get upset. I'll clean it more for the next 302 lecture. Get this just good so you can see some good contrast. I'm running low on paper towels out here, so I gotta be careful. Okay. Let's look at buoyant force. Fluid dynamics. Find the lid. There we go. Now, fluid dynamics is section 14.5. Fluid dynamics. Dynamics means motion, so fluids in motion. What we did before was fluid statics. Fluids weren't moving, and the properties of fluids as they don't move. Now, we're going to deal with ideal fluids. Now, of course, what is an ideal fluid? It's not a real one, but it's close. We do this because it's simpler than dealing with the real fluids and the way they operate. And it gets us close to what we want to do. So what we're going to say is an ideal fluid, that's what we're going to think of. And think of water as a pretty darn good ideal fluid. It's incompressible. It's incompressible. It's non-viscous. When you think of viscous, think of honey. So it doesn't have a resistance to flow. it basically friction free. No resistance to flow or say movement. Of course, everything has some, but we gotta walk before we can crawl. I said that backwards. We gotta crawl before we can walk, right? We gotta understand the ideal ones, and then you would get into like at a junior level course on fluid dynamics, compressible and viscous flow and honey and stuff like that. We're going to assume the flow is laminar. A laminar method, laminar state. So what is a laminar flow? It's smooth, straight line flow. And I'm going to try to show you the difference. Now, I haven't demoed this. Rule number 1 of physics teaching, always demo before you do it in class. So I'm going a little cowboy here on this demo, but hopefully it'll work. This model fails with significant fluid viscosity, like honey. Gasoline, when it gets cold, it kind of flows like honey. Oil does that way. Or turbulent flow. You want to think of turbulent flow, if you've ever been in the back of a boat and watching the water all kind of come together and make all the white foam and stuff around it and going all together like that. That's turbulent flow. I'm going to try to demonstrate the difference between laminar flow and turbulent flow. So I've got an electric match, and I'm going to hook that electric match up. I'm assuming my little connectors are still good, and they look pretty good. And what I'm going to do, try to light this electric match. And the idea is the electric match, take a match, a regular match. I had some at the house. I forgot to get them. Electric matches are more fun. We can do it when we want. It'll light, and then it'll start smoking. It'll go up straight, and then it starts getting curly a little bit. So right after this pops, I'm going to pop this electric match, and I have these because I use these. These we used, fireworks are ignited with this. Also, some rocket motors. We ignite using an electric match. The electric match basically burns some gunpowder. Then the gunpowder itself, slow burning gunpowder, ignites the motor. This doesn't have enough heat to ignite a rocket motor in general. But as it smokes, it'll go up. Then when it starts curling, that's turbulent flow. When it goes up straight, that's laminar. It goes up straight initially, and then air starts interacting on it after a little while, and that causes it. So if I've done everything right here, these are apart from each other. When I turn the jump starter on, here's my jump starter I got, which you can't see, but let's see if we pop this electric match. As you see, now that went out everywhere. The curling of it is definitely turbulent flow. Let's see. It spewed out in all directions, so that's why I didn't get any laminar. Let me check here just for a minute. I forgot about something I had. It looks, that showed you turbulent flow most definitely as it curled out, as it spewed out and started curling after it got pushed out by the electric match. Got one of these. So let's light something on fire. Take a napkin I can't use anymore. Let's light this on fire. Right? You put it out. So it goes up, it's straight. When it starts to curl, that's turbulent flow. Try not to push on it. It's going up straight. Yeah, that's actually good. After a little while, things interact on it. You get turbulent flow. Right at the beginning, it's laminar. Laminar flow. It's pretty cool. It's nice laminar flow there. Evidently, I got the barn door open here. It's not open there, so I got a little bit of. It's out pretty good now. All right, so turbulent and laminar flow. Hopefully, you're able to see the difference. Now, when you deal with moving fluids, there are really two things you got to worry about, and there's two basic equations that govern it. And one of them is called the equation of continuity. And this involves, see, there's a pipe that goes from here. So we've got fluid, some green, let's make it blood. It's going to be part like an artery to, necking down to a smaller one and stuff. So he's coming in and it's going out right here. So at this point here, we've got some area. We'll call this some area 2. Up here we got a lot more. We'll call this some area 1. And if it's circular, of course, you'd find the area from, the radius. And this would be R2 and this would be R1. And it's coming in with a certain velocity. The blood is being pumped by the heart. So it's got a certain velocity right here. Call that V1. And coming out, it's got another velocity, V2. So comparing to these 2 points, let's think what's happening. Well, you know what's happening. So you know what this velocity 2 is compared to velocity 1 because you've done this before. I don't look at my veins and arteries and see that. Of course you don't. But you do it with the water hose. What do you do with the water hose? And I happen to have a water hose around here. Let's see. Had to move the old go-kart. So this is where you would attach it on one into the pipe. Let's just assume it's done that way on the other way. So how do you make it? It's going to come out. It's going to drill. Bleh, right? Bleh, 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 bleh. It would just come out like that, right? If it was Dracula, it would come out like blah, blah, right? So how do you make it come out faster? How do you make it the flow faster coming out of this? Well, you put your thumb on it, right? And you put your thumb on it and make the opening smaller. If you make the opening smaller, you squirt your sister, right? Squirt your brother or squirt your parents. Whoever you want, right? Get